Representation turns text and images into an ordered sequence that the model processes. Tokenization creates that sequence of tokens. Embedding lookup turns each token into a vector the model can use. Positional methods tell attention how order works, and in modern models, that often happens inside attention. I'm Mehrdad, and in this lesson, we will follow that path from how inputs are prepared into attention. We will also look at failures that are often blamed on the model when the input preparation is wrong. Before we open the pipeline, start with a common debugging mistake. Many reports that say the model got worse are really interface problems. A wrong chat template can put roles or special token markers in the wrong order, so the model sees a different conversation than you intended. The tokenizer can produce far more tokens than expected, raising cost and cutting into the length limit. Positions can also go past the range the model was trained to handle. Those three look like the model quality dropped. Often the weights are fine, and representation should be checked first. How does text become something a transformer can process? The tokenizer converts the string into numeric token identifiers. Each identifier looks up one row in the embedding table, so a sequence of n tokens becomes an n by d matrix of vectors. That matrix enters the transformer blocks. Inside each layer's multi-head self-attention, the model builds query and key vectors, applies position information, and then forms attention scores. That position step happens inside attention in every layer. It is not added once to the embeddings at the start. We will explain that placement carefully on its own slide. For now, remember the stages: text, token identifiers, embedding lookup, then attention. If this lesson is useful, like the video and subscribe for the rest of the Transformers and LLM Systems course. Tokens are not the same as words. A modern tokenizer often uses byte pair encoding. It starts from bytes, learns which neighboring pieces to merge, and builds a fixed vocabulary. The same text can become fewer larger tokens, or many smaller pieces. Code and multilingual text often produce more tokens than everyday English, even when the text looks short. That token count changes cost, latency, and how much fits inside the length limit. Getting fewer tokens is not free. A larger vocabulary can shorten sequences, but it also grows the embedding table. So measure cost with the tokenizer attached to the checkpoint you will serve. The same model can look broken or correct depending on the chat interface. When the chat roles are out of order, an assistant turn can appear too early, the system message can be missing or in the wrong place, and the special token markers that should open each turn can be wrong or absent. Then the model is not seeing the conversation you think you sent. A chat template fixes that. It places system, then user, then assistant in a clear top-to-bottom order, and it wraps each turn with the markers that the checkpoint expects. So use the provider template, or the library call that applies it, instead of inventing the format by hand. If the answers look wrong, check the role order and special token markers first. Keep the template versioned with the checkpoint, and do not start by swapping the model. People use the word embedding for two different purposes, and that mix-up causes a lot of bugs. Both sides can start the same way. Token identifiers look up rows in a table, so n tokens become an n by d matrix of vectors. In a generative model, that matrix stays a sequence. It goes through the transformer blocks, and the language model head predicts the next token. However, in a retrieval model, the goal is different. The model turns a sentence or passage into one vector used for search. So do not take the token vectors from a generative model, average them, and expect a good retrieval embedding. Search and retrieval augmented generation come later in the course. Why does attention need position at all? Start with a bag of tokens. If order is ignored, the same tokens can be shuffled, and the model has no built-in way to tell one arrangement from another. Early transformers tried one fix: add an absolute position signal to each embedding row before the stack. That approach struggles when sequences get long, especially when serving goes beyond the lengths used in training. The lasting lesson is simpler. Attention needs a position signal so it can tell which token came first. Next, we look at where modern models put that position signal: inside attention. Rotary position embedding, usually pronounced rope, is the position method used in most modern language models. Token identifiers become embeddings, then enter the transformer blocks. Inside each attention layer, the model builds query and key vectors, and rope rotates those projected vectors by their positions. It does not rotate the value vectors. When those rotated query and key vectors are used to form attention scores, relative position can enter the scores. Rope is not added to the input embeddings before the transformer blocks. It is applied inside attention, in every layer. Even without an explicit position method, a decoder language model already gets sequence direction from the causal mask. In the attention grid, rows are queries and columns are keys. The lower triangle is allowed, while the upper triangle is blocked, so each position cannot look ahead to future tokens. That mask is applied before softmax, so future tokens never enter the next token probabilities. However, this is not a padding mask. A padding mask only covers empty filler positions when several examples share one batch. Even models that skip position encodings or mix them with rope still use this causal mask. We will go deeper on those designs in video 7. For now, remember this. The causal mask already carries order. The max length on a model card is not the same as proven usable length. Begin with the max length the provider publishes, the context window. That number is a contract for how far the system says you may go. Inside that is reliable run length. The request is accepted and the model finishes without a hard failure. Inside that is effective use. The model actually finds and uses what you placed across the window. Those three answer different questions. Doing well on perplexity for long text does not mean the model can find information placed far back in the prompt. We will cover how to test usable length on your own task in video 7. For this lesson, treat the number on the model card as a limit to test, not a guarantee of usable memory. Images also become an ordered sequence the model can read. The image is divided into a patch grid. Those patches become sequence tokens that sit beside text tokens in the model input. A vision path usually uses an encoder and a projector to place those vectors into the language model space. Even a short caption can come with many image tokens, so token cost rises and the context window fills faster. Multimodal rope is still rope on query and key inside attention, with extra axes for space and time. It is not added to the input embeddings before the transformer blocks. Full multimodal systems are covered in video 8. For now, remember this. Images become sequence tokens too, and those tokens still count against max length. Here are the 3 points to take away. First, representation starts at the product interface. The tokenizer and the chat template decide the sequence the model actually receives. If that sequence is wrong, the model is not seeing the conversation you intended. Second, generative embeddings and retrieval embeddings are different. A generative model keeps one vector per token for next token prediction. A retrieval model builds one vector for a sentence or passage used in search. Do not treat them as the same thing. Third, rope places position inside attention. It rotates the projected query and key vectors in every layer. It is not added to the input embeddings before the transformer blocks. When representation is wrong, the model can look broken even if the weights are fine. If this Transformers and LLM Systems lesson was useful, subscribe to Multi-Agent Academy and connect with me on LinkedIn. In video 3, we will compare the architectures that consume these sequences and explain why their differences matter. Thank you for learning with me, and I'll see you there.